I have you loud and clear.
Hello. Welcome. Science.
And that is to say,
physics,
medicine,
nature,
or
space, time,
the brain,
life, the universe.
Hello, this week we're exploding the science of volcanoes. Why do they erupt? What threat do they pose to planes? What impact do they have on us? And what do they do to our environment?
Coming up first, though, news that marriage cuts your mortality rate, what 800 million tweets have revealed about human moods, and why this sounds the way it does. I'm Izzy Clark.
I'm Chris Smith, and this is The Naked Scientist.
The Naked Scientist podcast is powered by ukfast.co.uk.
First up, living in holy matrimony might come at the cost of some nagging, but it could also save your life, as Marika Ottman reports.
Want to cut your risk of cardiovascular disease? Getting married might be the answer. 80% of all cases of cardiovascular disease can be attributed to identified risk factors such as age, sex, and smoking. But what about the other 20%? A team at Keele University has identified marital status as a possible risk factor that could explain that remaining 20%. I spoke with cardiologist Mamas to learn how getting married is good for the heart in more ways than one.
Often in my clinical practice, I have patients that come in and see me, and they say to me, the only reason that we've come and seen you is because our wife told us to or our husband told us to, which made me think that maybe marital status of a patient can give us additional information. That's why I decided to look at the relationship between marital status and future cardiovascular health in these patients.
Worldwide, there are many cases of cardiovascular disease, and with that, there have been many studies conducted to determine their causes.
What we did was a meta-analysis. So what that means is that we looked at all of the studies that have looked at the question of whether marital status is associated with cardiovascular disease, and then combined the results from these 34 different studies from all over the world, conducted in over 2 million patients to get our findings.
After assessing over 2 million patient cases, Mamas and his team discovered results that were rather shocking.
If you are unmarried, you have a 40% increase in the risk of developing cardiovascular disease or dying from coronary heart disease or stroke. We also looked at outcomes in patients or individuals with established cardiovascular disease. So, for example, patients that are admitted with a heart attack or admitted with a stroke. And we find that, again, marital status is associated with much better outcomes in the married compared to the unmarried patients. Particularly patients or individuals that are divorced seem to have a much higher risk than their married counterparts.
So why are unmarried people more likely to develop cardiovascular disease? Perhaps the answer lies in the vow, in sickness and in health.
I work as a cardiologist, and often, even today in my clinic, patients will always say, I developed these symptoms, I didn't think anything of them, but my wife or my husband, really pressurized me to seek medical attention. I think also there's lots of spousal pressure to adopt a healthy lifestyle. So often men in particular after heart attacks who were smokers will get a lot of pressure from their wives to give up smoking.
So maybe nagging is a good thing.
Yeah, perhaps. And I think, there's also other straightforward things like if you have a stroke, for example, you have great difficulty immobilizing sometimes. And so having a partner that can actually take you to your rehabilitation, to outpatient clinics and so forth, will really help in your recovery, whereas single people may not have this social network to be able to support them to do this. And we know that adherence to medications, i.e. whether you take your medications, is much greater in married patients compared to unmarried or divorced patients.
But let's say someone isn't married, but they're living with a roommate.
I think, social relationships are really important. Part of the question is, how close is that relationship with your roommate? I think that will impact on, the health benefits, but certainly any form of relationship would probably be better than, isolation. We know that social isolation is associated with worse outcomes for a number of different conditions in medicine.
So marry your sweetheart to save your heart. And say I do to cardiovascular health.
So sweet hearts lead to healthy hearts then. That was Marika Ottman speaking with Mamas from Keele University, and the paper they were discussing was published, rather appropriately, in the journal Heart.
Certainly is. Now, as our lives increasingly shift online and computers continue to take over the planet, hackers and spammers and other dodgy operators are finding progressively more ingenious ways to separate us from our cash. And their latest ruse is to steal your electricity. Not directly, but instead by getting your computer doing lots of power-hungry, complicated calculations, the results of which they then sell to make money for themselves, leaving you to pay the power bill. And they're hiding the system that does this in normal web pages and even online adverts, so it's really easy to fall victim without even realising. They call it cryptojacking, and I went along to the offices of web hosting company UK Fast, who've been monitoring the situation, to hear what they're finding.
My name is Chris Folkert. I'm the Director of Enterprise Technology here at UK Fast. Cryptojacking is the latest trend. Last year we saw a lot of crypto locker, where people were using cryptography to lock people's machines and then extract payment. This year it's changed to using their computers to generate the money automatically rather than trying to get customers to pay.
Right, so this is the whole concept of mining for bitcoins, isn't it?
Yes.
So I suppose we should explain, first of all, what actually is cryptocurrency and how does it work?
Cryptocurrency has been around for the last 10 odd years, and it's a different way of representing currency. Traditionally, it's gold coins. It was something that you could handle. Nowadays, people are moving to a more electronic form. So there's no inherent value to cryptocurrency. It's got a value because people have decided it does. And all it is a small packet of information that can uniquely prove as yours, and you can subdivide and trade with other people. And that's all done with cryptography.
And where do you get bitcoins from, or how are they made or minted?
So the easiest way people can get them is to now buy them online. There's exchanges where you can buy your cryptocurrency. All they are is effectively a payment from a computer as a thank you for processing some work. So Bitcoin is known as a distributed ledger. So it's basically an account book. And your PC will get a thank you for processing a part of that ledger and validating that it's true. But as there's more devices mining for it, the maths behind it gets harder and harder, so the value goes up because you have to do a lot more work to get the same reward.
One statistic I saw was that actually mining for Bitcoin, so doing these computer calculations, leads to the emissions of more CO2 from data centres than the whole of the country of Ireland.
There's been a lot of speculation around that. It certainly is a CPU-intensive operation. If you look at the people who are doing it semi-professionally nowadays, they have an extremely large number of arrays that are doing calculations all the time, and that does utilise a huge amount of electricity.
So if you can't afford to either meet that electricity bill, build a big enough computer or run a big enough computer, the simple answer is you basically steal someone else's computer indirectly via planting something on their machine that does those calculations on their machine without them knowing and does the work for you and then sends you the results. Is that basically what's happening?
Yeah, pretty much. The electricity costs are now at a point where there is a trade-off between whether it's actually worth mining some of these currencies. So now it is very much use someone else's resources, steal their electricity, and then get the coin for free.
So how are people doing this?
There's two main methods that people have started to adopt. They are getting you to open an email that opens up an application that crypto mines, and that sits in the background in your PC doing that. Most people don't notice it, other than the fact it will slow your PC down. There's now a trend in the last 6 months to doing it in browser, and this is the bit that's got slightly more troublesome because it's so easy to exploit. And that is where websites are installing something called JavaScript. It's a bit of a software inside their web page that runs in the background, and it uses your spare CPU cycles to generate the coin for them.
Oh God, that's really sneaky. So by visiting a website, you don't even realise you're actually trying to earn some money for the website owner, and it's basically your electricity bill that's paying for that.
Yep. So recent scans of the web found about 33,000 sites already, and that's just well-known sites that have started doing it in the background.
Wow. When you say well-known, as in the kinds of sites that your average web user would visit?
Yeah, they're not necessarily going to be the high brand name ones, but a lot of the ones where you're getting content for free. So free services are sometimes now subsidizing themselves with some of the coin mining.
And it doesn't compromise the website performance?
It does, and that's where a lot of users are pushing back. There's been some instances where it's been the website owner that's been publishing the JavaScript, and that has had an impact. It can dramatically slow down not just your browsing experience for that, but if you've got any other tabs open as well, them as well. But what we've also seen is some people surreptitiously putting them into adverts. So the ones that pop up on your webpage, they will be doing the mining, but it drags the performance of the main website down as well. And that can be unknown to the website owner because they're not necessarily controlling their adverts.
How would a person listening to this diagnose that they may have this problem?
The biggest telltale sign is your PC will slow down. Unfortunately, that's not unique to cryptojacking. That could be anything. But if you notice that everything's started to run very slowly, either when you've got specific tabs open or you've got an application open, you can just go into Task Manager, have a look at your CPU, and it'll show that it's pegged at 100%.
So is it relatively easy to treat?
Yes, that's the good news, is a lot of the cases that are out there now are easily picked up by antivirus software. They will either block it automatically or tell you that the threat's present. At the same time, it stops these problems.
Right, might go home and do an antivirus update then. That was Chris Folkard from UK Fast.
Terrifying, though.
Absolutely,
The
I'm
ingenuity
terrified.
of this, amazing. And my electricity bill is making someone some bitcoins. That's wonderful.
From baffling British weather
Sideways spines of the vertebrae coming off here.
to looking at a cheetah from the inside out, games making their way to the clinic, and what to eat in your garden. The Naked Scientists In Short podcasts bring you a top-up of short, compelling science stories. Listen and download for free at nakedscientist.com/short or subscribe to Naked Specials wherever you get your podcasts.
Now, still to come on the programme, what Twitter can teach us about people's moods, and we're also getting the inside story on the science of volcanoes. Before that, though, Izzy, hopefully this is a sound with which you have some familiarity.
That's a very annoying sound of a tap dripping.
Yes, it is indeed dripping water, but actually it turns out that the science behind why this happens is a lot more complicated than we first thought. And this week, scientists at Cambridge University have solved the riddle of the reason why a drip sounds the way that it does. And with us is engineer Anurag Agarwal, who actually made the discovery. Welcome to the programme. Why on earth were you studying water drips?
I was visiting a friend in Brazil, and it was the rainy season. It was raining very heavily. The bedroom I was in had a small leak. And what my friend did was placed a bucket underneath, as one would normally do to collect the water. And at the beginning, everything was fine. But after about half an hour or so, I started to hear the annoying plink noise that you hear with the dripping tap, let's say, in your sink. So initially, this was very annoying and kept me awake. But then I quickly became curious. I wanted to know why it was making this loud sound.
And critically, why the sound had changed when the bowl was empty, you didn't get a sound. And then
Exactly.
as it got a threshold amount of water in it, it began to make the plink plonk noise that you get.
Yes.
And so the physicist and engineer in you kicked in and said, I have to design an experiment to work this out.
That's right. So we advertised it as an undergraduate project, and we found a smart student, Sam, to work on it.
Now, you brought us a demo. Bowl, water, syringe. What are you going to do with them?
Yes, I've got them here. So I've got a filled bowl with water, and I've got a syringe full of water. And what I'm going to do is I'm going to squeeze the syringe and release drops into this bowl full of water.
Before you do it in the water, though, you did say that when you were in your bedroom in Brazil, that when the bowl was empty to start with, there was no sound. So we'd better test that first. So
That's right. So I have an empty bowl here, and if I squeeze my syringe in this, I'm just about to do it. The first drop is coming down.
all right, we're listening really carefully,
It's hit.
and I can't hear
Second
anything.
drop,
No.
third drop, fourth drop. So as you can
Okay.
see, this is very silent.
Proved by experimentation. I believe you. So then the bowl gets full.
So now the bowl is full, and I'm going to do the same thing again. So I'm squeezing now. First drop.
Yeah, well, I'm definitely hearing the noise. Can I ask you to try something? Because you're doing nice little individual drip, drip, drip. What happens if you do a more rapid stream?
So if I do this.
Now that is different. That's louder. Is that the same thing, but just many, many times over, so it sounds louder, or is there something else exciting going on?
The mechanism here is different. So we have just finished the research for this, and it's about to be published.
Ah, so you're not going to give the game away?
No, you'd have to invite me again.
How did you then go about modelling that then, in order to work out what is going on?
This is the interesting thing. Then when the water drop falls on a hard surface, it makes almost no sound. But at the same time, when it's falling on a soft surface, it's making a lot of sound, and an annoying sound. This is counterintuitive. So what's happening is when the water drop falls on a soft surface, like the water surface caves in because of the mass of the drop falling.
Oh, you mean the actual surface sinks a bit under
Yes.
the momentum of the falling drop?
Exactly.
Right, okay.
And then what happens is that this cavity that's formed wants to close because of surface tension. Water wants to get back to its original level. But it does so very quickly. And in doing so, it entraps an air bubble underneath. And this air bubble oscillates or pulsates at 5,000 hertz, which is 5,000 times a second. And that's the source of sound that we hear.
And it's right in the middle of speech frequencies, so we're actually quite tuned into that.
Actually, it's in the middle of the annoying speech frequency, which is between 1 kilohertz and 5 kilohertz. So other examples would be a baby crying, which is in that frequency as well.
It's very elegant you've been able to find out how this works, but can you extrapolate this and do anything useful with the model?
So one thing we can do with the model is to predict the amount of rainfall on an ocean, because once we know the frequency that we are measuring, we can tell what the raindrop size is, and from that we can estimate the amount of rainfall.
So what, would you put a hydrophone, a microphone underwater and listen to the rain falling?
Yes,
patch of ocean then?
Exactly, that's what we would
So
do.
how do you resolve where the rain is falling? Because the water is going to transmit vibrations from all over the place, over a big area, small area. How do you resolve all of that?
Localization is hard, but we can tell the total amount of rainfall. So we can do a sum of all the rain that's falling.
Forgive my ignorance, but is that a big problem facing marine scientists and hydrologists then, trying to work out how much rain falls at sea? Because if there's no one there to measure it, it's a little bit of a who cares situation, isn't it?
But if you're interested in, the total amount of rainfall in a season, and normally we do it over land in a certain place, then that could be interesting. But that's not what motivated us.
No, indeed. Any other applications, or is apart from getting someone a first?
That was the best project in the year, so the student was happy.
I'm not surprised. Very, very exciting.
But there is another application, which is that to synthesize sound, it's very hard to synthesize these kind of sounds. That's because you would think that most of the sound is coming from the initial impact when the drop falls on the water surface.
Yeah.
But from what I said, that's not what happens. That initial impact is completely silent. It's only when you get this bubble entrapped underneath, which is a few milliseconds after the initial impact, do you get the sound.
So does that mean then it's really hard to make an artificial raindrop sound?
Yes, because people up to now didn't know how to make it.
They were doing it wrong?
Yes.
So you can solve that?
Yes.
So can we look forward to then much better sounding rainfall made artificially in Hollywood movies and cartoons?
Yes, absolutely.
So have they licensed this? Have you protected this? Or can everyone just read your paper and rip this off now?
I think it's pretty easy.
Right, well, I'll just write that down, Izzy, for after the programme, and we'll go and work on that in the office.
I've made notes. I'm already on it, Chris.
Anurag Agarwal, thank you very much. Pleasure to have you on the programme.
I'll never listen to a leaky tap in the same way again. But first, with how a flame-proof spacesuit eventually brought us better building materials and even the roof of the O2 Stadium in London. It's time for this.
What happens when the science and technology of space comes down to Earth? Welcome to Down to Earth from the Naked Scientists, the mini-series that explores the spin-offs from space technology that are being used on Earth. I'm Dr. Stuart Higgins. This episode, how materials used in spacesuits developed for NASA for the Apollo missions continue to be used in stadium roofs around the world. January the 27th, 1967. A fire breaks out during testing of the Apollo 1 command module, the first of the missions aiming to take astronauts to the moon. Spreading rapidly through the flammable materials inside the spacecraft, the fire kills the 3 astronauts on board. The tragedy led NASA to search for new fireproof materials for their spacesuits. Nylon had been used throughout the command module but had melted during the fire, and the existing spacesuits failed to provide adequate protection. A solution was proposed by 2 companies working with NASA, a new kind of fabric based upon woven glass fibre and coated with the non-stick plastic polytetrafluoroethylene, otherwise known as Teflon. They called the new material beta cloth, and it formed the outer shell of the updated spacesuits, giving 10 times greater fire resistance compared to what had been before. And while spacesuit materials have moved on since the Apollo era, beta cloth found a new lease of life back on Earth as a construction material. Walter Bird, an aeronautical engineer, realised the potential of beta cloth as an architectural building material, and in 1956 formed a company to take the tech further. The company specialises in tensile structures, where the building materials are continuously held in constant tension, and they're most commonly seen today as the curving tent-like roofs on structures like the O2 Stadium in London and many other sports stadiums around the world. The tightly woven glass fibres give the material its structural integrity, while the Teflon coating reduces the ability of dirt and grime to stick to the roof, allowing most of it to wash off when it rains. The Teflon polymer is made up of a long chain of carbon atoms, each attached to atoms of fluorine. The configuration of electrons in the fluorine atom make it highly electronegative, meaning it can strongly attract other electrons towards it. It's the incredibly strong bond between carbon and fluorine atoms in the plastic that gives the useful non-stick properties. Also, when used in beta cloth, Teflon's white colour has the advantage of helping to reflect sunlight, stopping things from getting too warm inside buildings. The flexibility and strength of the material, along with its rapid installation, allows architects to explore different and interesting designs in their structures, and has furthered its use. So that's how a material originally developed for spacesuits for Apollo astronauts has become a widespread building material throughout the world. That was Down to Earth from the Naked Scientists. My name is Dr. Stuart Higgins, and you can find more episodes online at nakedscientist.com/down-to-earth.
Thank you, Stuart. And next time on Down to Earth, Stuart explains how a technique for making fresh water in space ultimately led to scratch-proof lenses down here on the ground.
Definitely going to be worth a look. Now, Twitter might reflect the mood of the nation as we collectively share our thoughts with the masses, but can we use this data to answer serious scientific questions? That's what a team at the University of Bristol wanted to find out. So, for over 4 years, they collected tweets every hour from the 54 largest cities in the UK. They then worked out what categories of words were being uttered at any moment, and that provided them with an indication into people's moods at the time they were tweeting. Georgia Mills got the hashtag story from the study's author, Nello Cristianini.
The big surprise for us was that there are indeed two different thinking modes. One morning-oriented, one more night-oriented. A morning mindset focused on power, drive, achievement. And that is a very strong signal that peaks 7 a.m., 8 a.m., 9 a.m. in the morning. And as the day progresses, we see a change in this. And by the time you reach the late evening, you start seeing a lot of he and she pronouns, male and female references. You start having negative emotions, swearing. And as you go on into the middle of the night, we have the moment when people talk about death. And just before the sunrise, this is the moment when the religious topics peak. And then the sunrise starts and everything, the cycle starts again.
I think we can all relate to the existential dread in the middle of the night. But how did you pick apart the fact that these are trends happening to the same people? Because could it be that the people who are awake and tweeting at 6 a.m. are just more driven, and the people who are awake and tweeting at 3 a.m. are just more concerned about death and things like that? Could it be this is just when different people are choosing to tweet?
Absolutely right. So obviously this is not the same one person tweeting. There are different people tweeting, and we are sampling them. One could say there are different types of people, and some of them are active at night, and that's entirely possible, and it's hard for us to correct because we anonymize. However, I would argue that isn't this the same point? Then you can ask right away, why are those people who are interested in darker topics active at night? And why are those people interested in social concerns active in the evening after dinner? So in a way, we are coming back to the same question again. Why would they be active at different times?
Have you got any ideas?
Well, we have conjectures, but we don't have anything. So this study really is carefully pointing out that this happens. As for causation, that's difficult. So one thing we did, we tried to ask a follow-up question. Is it possible to summarize all this variation and explain it with a few factors? And we found that just postulating 2 hidden factors accounts for nearly 80% of all the variation. And they are cyclic, of course. One peaks at 6, 7 a.m., the other one peaks at 3 a.m. They actually behave like some of the hormones we have. So although we cannot prove anything, we do observe that this variation do correlate to some of our hormones as well.
Right, so this could be a flag that maybe it's our hormones driving this change, but further work needed.
Further work is needed, but we do have this suspicion. But for this paper, what we can report with confidence is the empirical observation that these things are cyclic. They have a 24-hour cycle, and this is statistically significant.
How many tweets would you say in total you analysed?
800 million tweets.
Oh, wow. Yeah, quite a big number. So is this going to change how we do research, what you've done here? Is this just the tip of the iceberg?
Yeah, my hope is this, that we can start using these things in a good way. You could repeat the same study by looking at different types of data. For example, in the past, we've been looking at the log of the queries in Wikipedia. What are people searching for in different seasons? And we find very strong seasonal patterns in the queries. So data is becoming available. It's open. And if you have the right scientific question, you can design a study and get an interesting answer.
What kind of questions would you like to ask?
Well, in this moment, I'm still looking at seasonality and daily cycles of emotions and thinking patterns. Previous studies we have done show that there is an increase of negative emotion and sadness in the winter, and we try to look at mental health. Many years ago, we did demonstrate that you can use this to detect flu epidemics. So we are just exploring what is possible.
Be interesting to see if they're actually going to look at the tweets that get issued during the World Cup, won't it? That was Nello Christianini speaking with Georgia Mills, and the paper describing those studies was published in PLOS ONE.
And if you'd like to find out more about any of the stories we've discussed, we've got all the transcripts and the links to their paper on our website. That's thenakedscientist.com.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
You're listening to us here on The Naked Scientists. It's Chris Smith and Izzy Clark, and it's time now to get into the flow of the second half of this week's show.
Oh my God. Oh my God. We could hear the lava exploding right from the house.
One of the world's most active volcanoes, Kilauea on Hawaii, is also still erupting. But despite the almost constant eruptions, Hawaii has seen no fatalities.
Volcanoes have been in the news a lot recently with eruptions in Hawaii and Guatemala. So this week we're taking a look at the impact that volcanoes and eruptions can have on the environment, technology and our lives. Jess Johnson is a volcanologist from the University of East Anglia. She's with us. Quick 101 then, please, Jess. What actually is a volcano, apart from just what we see, obviously?
A volcano happens because there is magma under the ground made up of molten rock and gas and small crystals of rock. And that magma is going to be less dense than the surrounding crust, the surrounding rock. And because it's less dense, it tries to get to the surface. Once it gets to the surface, it erupts as lava, as an explosion, a gas, ash, and that is what we call an eruption of a volcano.
What powers a volcano? Where does it get this heat from?
The thing that's actually causing the magma, the melting of the rock, it could be due to decompression. So where the rock is coming to the surface, it has less pressure on top of it, and that causes it to melt. Or it could be a chemical reaction with the addition of water. When you add water to a rock, it lowers the melting point, and that might melt the rock. Or it might be a bit hotter than the surrounding area, and that might also melt the rock.
And apart from the hot rock that we can see, what else is issuing that we can't?
Mostly gases. There are lots of different gases that come out of the magma at different depths as well. So the gases that we usually associate with the eruptions are carbon dioxide, sulfur dioxide, steam. And then if it's an explosive eruption, you might have tiny particles of the lava, which we call ash as well. So that would also be caught up in the plume.
And how do those gases get in there in the first place?
The gases are dissolved in the rocks, and as the rocks melt and become less pressurized as they rise through the crust, different types of gases will come out of solution at different depths. So by looking at the gases, we can tell how deep the magma is.
Why do volcanoes happen where they happen?
So the Earth has a thin crust on the outside, which is what we live on, and that crust is split up into plates, which we call tectonic plates, and they move around on the surface of the Earth. At places where they move towards each other or apart from each other, that's where we're likely to get volcanoes.
What triggers them to go off?
That's a very good question. We don't know exactly what causes an eruption to start when it does, but we do know that there are some triggers. For example, if there's a new batch of magma that gets pushed into the magma reservoir, that can cause a chemical reaction. Ultimately, gas is what drives most eruptions. If there is gas trapped under the ground, then it will try to get out, and that's what causes an eruption.
How good are we at predicting or forecasting when an eruption might happen?
We're okay. We're getting better. We monitor volcanoes, particularly volcanoes that are near populated areas, with seismographs, which measure motion of the ground. And so what we're looking for there are small earthquakes, because when the magma is pushing its way through the rock, it will crack the rock and cause lots of small earthquakes. So if we can monitor where those earthquakes are, we can tell where the magma is going. That magma might also deform the surface of the ground, and so we can monitor that with satellites.
You can see that, can you?
Yes, you can, absolutely. In fact, in Hawaii right now, the surface of the caldera, because the magma has been withdrawn from the summit, it's subsided by tens of meters.
Really? So that you
Yes.
can actually physically measure the ground buckling and changing
Yes,
shape
absolutely.
as the magma moves in and out?
Yes, absolutely.
And those movements are then used to make predictions?
Yeah.
Anything else that you can look for? I mean, what about gases coming up? Because if you've got magma and things moving, presumably the gas composition could change. Can you look at that?
Yes, absolutely. So as I said before, because the different gases come out of solution at different depths, we can look at how much gas, which gas, and where those gases are coming out to tell us where the magma is moving.
And what happened in Hawaii, is that comparable with what happened in Guatemala?
Not really. It's the same in that there is magma under the ground that is trying to get out, but they're two very different volcanoes. In Hawaii, the magma is a lot runnier and a lot hotter. That allows the gas to escape, and it allows the lava, once it's out of the ground, to continue to be runny, which means that we don't get so many explosions. Whereas in Guatemala, it's a different type of volcano caused by water being dissolved into the rock. That's what's causing the magma. And so there is more gas, the lava is very sticky, and that's why the gas can't escape and pressure builds up, and that's why we get a big explosion. This sort of activity, volcanoes are quite local processes. There aren't any connections between these two volcanoes.
Jess, thank you very much. We must leave it there. That's Jess Johnson. She is from the University of East Anglia.
Now, as we've heard, when a volcano erupts, there's a plume of gas and a stream of magma. And whilst magma can leave a trail of destruction, the volcanic gases also have a huge impact on our environment. This is something of interest to volcanologist Evgenia Ilinskaya, who has seen her fair share of eruptions.
My favourite story is probably a relatively small eruption that happened in 2010 in Iceland. This little eruption was in the middle of nowhere up on the mountain, and at this point in time it was still very much winter in Iceland, so it was very snowy. And we reached the eruption site at about the time then when the sun was coming up. So you had this virgin white snow and huge red lava fountains coming out straight from that snow, and black ash deposits put down around the volcano. So it was just a combination of colours. It was white and red and black, and it was just an absolutely fantastic scene, and it was making these sounds like an old school steam engine, a train coming past. I'm not particularly religious myself, but that scene was something you really felt in presence of something bigger and much more amazing than anything humans could ever make.
Evgenia's research focuses on volcanic gases as a way to monitor volcanic activity and its impact on the environment and the atmosphere. And it turns out volcanic gases are rather important when it comes to attempting to understand these mountainous pressure pots.
They can first of all tell us what is happening underneath the volcano. They can tell us whether molten rock, or magma as we call it, is moving towards the surface, if there's fresh magma being injected into the volcano. Once an eruption starts, we can use the gas to measure how big the eruption is, if it's becoming smaller, and so on and so forth. Some of the most abundant gases in magmas are actually water, carbon dioxide, and then sulfur dioxide. And then sulfur dioxide is something that you might hear volcanologists talk about a lot. It's a very important gas because it's relatively easy to measure, but it also has quite important environmental implications because it can be quite toxic.
Now, sulfur is a complicated beast and can exist in many forms. In volcanoes, it comes out as hydrogen sulfide, which actually smells like rotten eggs, or more commonly, sulfur dioxide, which is acidic. It can sting your throat, your nose, and your eyes, and is definitely something to avoid. Plus, it takes its toll on the environment.
If people remember the London pea soup fog back in the 1950s, that was actually caused by sulfur dioxide, which was being emitted by coal-burning power plants. But volcanoes definitely emit this. You can visually see it in the atmosphere. It sort of tends to be a blue, brown, grey cloud, and you can really see impacts on vegetation. So not a lot of plants can survive in this kind of environment. Sulfur dioxide can impact climate. It tends to happen in very, very big explosive eruptions. So think about Pinatubo eruption in the Philippines in 1991 or El Chichon eruption in South America in the 80s. So these are huge eruptions, and the eruption column goes up to tens of kilometers up in the stratosphere, so higher up than planes even fly. And if that happens, gases, in particular sulfur dioxide, can stay up in the atmosphere for very long periods of time, so months or years. And in those scenarios, we can start to see climate impacts around the globe. So actually what happens is that sulfur dioxide, with time in the atmosphere, gets converted into tiny, tiny particles. And those particles reflect incoming solar energy, making the climate actually cooler than it was before. Living organisms that are very sensitive to even small changes in temperature will react differently, or habitats can start to change if it's a really long-lasting effect.
Carbon dioxide is also released in a volcanic eruption, and we hear so much about it in the news. So could this be having an effect on climate change?
Carbon dioxide is one of the very common gases in volcanic emissions, and it is a greenhouse gas, which means overall it would warm the planet. And that is the reason our planet is warming at the moment, is because human activities are producing so much carbon dioxide. In comparison to how much human activities are producing, volcanoes are producing actually very, very little carbon dioxide, something like only 2%.
Ah, right. So we're causing more damage then. But is there any way we can use volcanoes to our benefit?
So it's very important to remember that volcanoes are not just destructive forces. So while volcanoes produce some carbon dioxide, they can actually be used to capture carbon dioxide, so removing it from the atmosphere and thereby reducing the effects on climate that humans are having. So this is something that's being experimented on in Iceland very successfully, where they're taking carbon dioxide out of the atmosphere and pumping it back into the volcanic rock and making it stay there. Another very interesting way of possibly using volcanoes is people tend to like living on volcanoes because volcanic soils actually are quite fertile. And also in hotter countries, living up on the flanks of higher up on the volcano means that the climate is a lot more pleasant. And a lot of plants are grown high up on the volcano flanks. For instance, coffee is produced in a lot of countries with active volcanoes.
And that's not all. Volcanoes produce a lot of power, and this can then be used to heat homes and water for those nearby.
Geothermal energy works when you have heat coming from molten rock deep down in the ground that is heating groundwater around it. And this groundwater can be several hundreds of degrees hot. So this superheated steam can be taken out of the ground and piped to communities and either just be used to then heat cold water to use it for showers, etc., or to drive steam turbines to generate electricity. It's fantastic to see this where it's well set up. In Iceland, something like 9 out of 10 homes are heated entirely by geothermal volcanic energy. Energy like this is very, very cheap. of course, volcanoes, we can only use very little percentage of the energy that volcanoes are able to generate. So there's a lot more to do with volcanoes and discover how we can harness the energy much better.
In fact, we were hoping that Evgenia would be live on the show, but she's actually had to go to Guatemala to see the Fuego volcano for herself. That was Evgenia Ilenskaya from Leeds University.
You're listening to The Naked Scientist with me, Chris Smith, and with Izzy Clark. If you'd like to get in touch with us here on the programme, it's chris@thenakedscientist by email. You can tweet at Naked Scientist. We also have a Facebook page. You look up facebook.com/thenakedscientist. Still to come, we find out how eruptions have shaped history. But before that, were you trying to go anywhere in 2010?
Hello, good morning. British airspace is shutting down for the first time since 9/11. Within the next hour, all flights in and out of UK airports will be suspended because of the huge volcanic ash cloud from Iceland.
Now, I was certainly a victim of that. Many others remember being stuck and grounded at very long queues at airports because no one went anywhere. In fact, that became the largest global air traffic shutdown since World War II. And it happened because an Icelandic volcano called, and I'm not going to say this, instead I'm going to defer. And well, let's ask our panel of people who are here with us. Izzy, would you like to say the name of the Icelandic volcano that exploded in 2010 and grounded lots of aeroplanes?
No.
All right, then. Let me try and say Jess. Jess Johnson, would you like to have a go at the name of it?
Eyjafjallajökull.
Shall we see if she's right? Because I chickened out and I found YouTuber The Magnus Effect, who actually published a video in the wake of all of this because I think he was sick and tired of hearing people mispronouncing it. So actually this is the name of the volcano pronounced correctly.
So here it goes. It's Eyjafjallajökull. That's Eyjafjallajökull.
Got that? Anyway, it was that volcano, and it ejected ash to a very high altitude, and the ash can actually cause catastrophic damage to aircraft engines. But how does it do that? Well, we've got with us Anna Young. She's at the Whittle Lab in Cambridge. Welcome to the programme, Anna. What actually is in that ash that is going to potentially damage an engine?
Basically, the ash is sand, and sand can cause quite a lot of damage to the engine on its own in the first place, but because of its larger surface area, it can melt more easily, and when it turns into glass in the hot parts of the engine, that can cause really, really big problems.
These are jet engines that we're dealing with here. That's what you work on. So Can you just explain very briefly how a jet engine works?
Sure. So when you're walking up to your plane, the part you can see is the fan, big set of spinning blades, and the job of the fan is to pull the air into the engine. And about 90% of the air is just goes through the fan and then out through the nozzle at the back, where it's pushed out quickly, and that jet going backwards creates thrust to drive the engine forward. Now, the job of the rest of the engine is to use the other 10% of the air to drive the fan. So the air that's not gone just through the bypass goes into the compressor, where it gets squeezed to a much higher pressure, and then it goes into the combustion chamber, where we burn fuel to add energy. And next we've got hot, high-pressure air, and that goes through the turbine, which is another set of spinning blades that takes energy out of the air and uses that energy to spin the fan and the compressor. So the turbine uses hot air to drive the fan, which produces thrust to drive the engine.
I went to a talk by someone from Rolls-Royce and they summarised it and said it's suck, squeeze, bang, blow. So
Yeah,
it sucks
something
air
like
in
that.
at the front, squeezes it very hard and gets it hot, chucks a load of fuel in which burns, and then they extract energy at the back end, having blown the gas stream out to then drive that fan. But I suppose one should point out that the gas stream in there is at very high temperature, isn't it? It's like 1,500 degrees C inside the engine when the fuel's burning.
Yeah, so at the entrance to the turbine, the air is, as you say, about 1,500 degrees, and that is hotter than the melting point of the turbine blades.
So the engine's running at a temperature beyond its melting point. So why doesn't it melt?
What we do is we take some air from a cooler part of the engine from partway through the compressor, and we drill tiny little holes in the turbine blades, and we blow that cool air through, and that cool air creates a film that keeps the turbine just under its melting point, basically.
So you're protecting the surfaces of the blades with a very thin cushion of slightly cooler air.
Exactly.
So any incoming gases are sort of going to ride over the surface of the blade without touching it.
Yeah.
So if I chuck in a whole bunch of sand and volcanic dust, what does that do to the system?
It's likely to turn to glass because, as well as being hotter than the melting point of the turbine blades, that part of the engine is hotter than the melting point of the ash. So we get glass, which clogs up all of those little holes, and then we won't have any cooling air, and the turbine will melt.
And then you get a sort of hotspot on the blade.
Yeah.
And what will that do? Cause it to weaken or change shape, deform, distort?
Yeah, I think it'll all happen pretty quickly at that point, and the blades will start melting. So then you haven't got a turbine to drive your fan. The other thing that happens is that air has to go somewhere, and where all the rest of the air from the compressor goes is the combustion chamber. And we have the wrong mix of fuel and air. So that can make the fire in the combustion chamber go out, and then you've basically switched your engine off.
And then you lose power catastrophically.
Yeah.
So given that we know this, what can aircraft operators do to minimise the damage to their engines? Just not fly?
Essentially, yes. In my lab, we spend a lot of time simulating the flow of air through the engine. You could do that, and people have done it, where you add in the flow of the sand as well. But the problem is that is a very complex process and a very big calculation. So probably by the time you've got your answer as to where the glass is going to form, your volcano stops erupting because you need such a big computer and you've got to leave it for so long.
But engineers can say, oh, don't fly when there's a volcano, but pilots may not be able to avoid one if one suddenly goes off. So under those circumstances, obviously they could try to avoid the ash cloud, but there are potentially going to be particles going into the engine. So what does that do? Just shorten the lifetime of the engine?
Yeah, so if it's just a case of more straightforward sand, which isn't going to melt, then the front part of the engine bears the brunt of that. And if you've ever been on the beach on a windy day and the sand gets whipped up into your face and it stings, if you imagine doing that at 600 miles an hour, that's what happens to the fan and the compressor. So the sand particles blast the blades. We design the blades very carefully. The tolerance on them is around the width of a hair. And then you're blasting random bits off with sand. Suddenly you don't have nice, smooth shapes that you designed, and the air won't pass as smoothly through. So you start losing efficiency, start using more fuel. If that's a commercial plane, that means you've got to pay more for your ticket, and probably you've got to start replacing bits.
Presumably, if you do end up with this sort of damage to the engine, this can be monitored and you could replace the blades that have worn.
Yes, you can. And one of the things that we do in our lab is we look at different forms of damage and see when is it bad enough that it needs to be replaced.
Yeah, so you basically know what the safe threshold to operate on is. Thank you, Anna. That's absolutely brilliant. Anna Young from Cambridge University's Whittle Lab.
Jess Johnson is also here from the University of East Anglia. So what about other technologies? Can volcanic eruptions affect what's going on at home as well?
They can, yes. So people who live near volcanoes probably do have to deal with some of the issues associated with them on a day-to-day basis, particularly if there is ash. It could be drawn into their electronic equipment. So your computer usually has a fan to cool it down in the same way that it could damage the jet engines, but not quite the same way. But the ash can clog up the computers, damage the computers, clog up air conditioning units and things like that. Ash also acts in a very strange way. When it gets wet, it gets quite heavy and almost cement-like. And so if you have an accumulation of ash on your roof or in your gutters and then it gets wet, then it can be very, very heavy. And there have been cases of people that have flat roofs, those roofs collapsing under the weight of the ash.
My goodness. And so obviously if we have an eruption, all of that gas and that ash can get redistributed over the globe. So can that also then move on to other areas and perhaps impact people's lives in other ways as well?
Yeah, absolutely. Depending on the size of the eruption, the ash column can get into different layers of the atmosphere and be distributed. It can affect the climate and it can affect crops as well.
And while we're talking about sort of gases and things, Jess, there have been reports in the past of volcanoes sort of belching up gases which then, being heavier than air, flow down into valleys and settle in low points and asphyxiate people. Is that just apocryphal or does that happen?
That does happen, yeah. I think the famous example was in Cameroon where there was a bubble of CO2 that got released from a volcano that had a water lake inside it. And because CO2 is one of the big gases that is released from volcanoes and it is heavier than air, it does just settle in a valley and people died because there wasn't any air to breathe, there wasn't any oxygen.
When you talked about mud just now, I wondered if you were also going to talk about the manifestation that's happened in Guatemala with mud flows.
Absolutely.
Because one of the things that Izzy was talking about was the Iceland eruption and the fact that there's a lot of snow. And so you've got a lot of heat with a lot of snow creates a lot of water. So you get this toxic combination of mud formed because you've got ash with water and the whole thing turns into a big catastrophe.
Yeah, we call them lahars, and they're a very common phenomenon. What happens is it can happen during the eruption. If there is an eruption during a heavy rain or a monsoon, you can have the water and the ash mixed together and cause a very fast-flowing mud flow, which can be very damaging. It can happen during the eruption, or it can happen at a later date if the ash is accumulated on the volcano and then there is an addition of water, so ice melting or a rainy season or something like that. The ash can be remobilised, can cause big landslides and mud flows, and as I said before, this stuff is like cement, so it can be really, really damaging.
Yeah, absolutely. Now, what about some of the gases that get into the atmosphere? We heard about global cooling, and what are some of the problems with the gases that are released as well? Because we heard about asphyxiation, but can they poison crops and things like that?
They can, yeah. Sulfur dioxide, one of the main gases that's released from a lot of volcanoes, when it mixes with water, it causes sulfuric acid, and so that can cause acid rain, that can erode metal and can also poison crops and livestock. So people who live downwind of Kilauea, for example, will be very familiar with what they call VOG. It's volcanic fog made up of sulfur dioxide.
Thanks very much, Jess. That's Jess Johnson from the University of East Anglia. But that's actually just some of the damage that an eruption can cause. Also on the show is seismologist Lucy Jones from the California Institute of Technology and author of The Big Ones, How Natural Disasters Have Shaped Us. So, Lucy, perhaps we should start with Pompeii. What happened there and what have we learnt from this eruption?
We all have the image that everyone was buried in their homes and died because we found those corpses when Pompeii was excavated. But actually, the eruption began with what's called the Plinian eruption, where the gases and ash head high up into the atmosphere. It turned everything black. It terrified people. And we know that about 90% of the people left during that period and survived. About 10% said, hey, rocks are falling on your heads. I'm staying in my home. And then were trapped there when what's called a pyroclastic flow came through, which is when the gases lose the impetus up into the atmosphere, and as they're heavier than air, they flow down at tens of kilometers per hour, sweeping through and burning everything on touch.
Now, how do we know how many people this actually affected?
Well, the Romans had decent tax records and numbers of people that lived in the area, and we can compare it with the number of corpses that were actually found in the excavation.
Now, throughout the show, we've also heard about these gases that are thrown out after an eruption. So how far can they travel globally? I mean, does it only affect just the people near that eruption?
Oh, absolutely not. It depends upon the explosive force of the volcano and how far up into the atmosphere they go. But as long as they aren't just at the surface, like we're seeing, say, in Hawaii right now, they get up into the atmosphere, they travel over. And in fact, in 1783, there was a massive eruption in Iceland. It was called the Laki eruption. The gases that came out from there essentially poisoned all the crops and animals in Iceland. They were both fluorine and sulfide gases, and the only thing to eat had to come out of the ocean. And the whole country of Iceland came very close to extinction. But then the gases traveled on and moved out over Europe. But now the gases were much more intense and concentrated. And our estimate is actually that 23,000 people died in the summer of 1783 just in the UK. Comparing death records of that summer with other summers, reports of a fever and burning throats. And looking back, it's like, okay, they were being poisoned by these gases in from Iceland. And then there were further deaths across Europe, so they can travel a very long ways.
Gosh, are there any other knock-on effects? Like we heard about this global cooling. So can that cause a big problem?
Oh, it can be huge. Once you get out of the immediate Earth surface, you get into the atmosphere, travel over to Europe. If it gets up into the stratosphere, then it can travel around the world. And in the stratosphere, it's much drier. And therefore, these particles, which actually are heavier than air and in the lower atmosphere get washed out relatively quickly, can last for years up in the stratosphere. So again, back in 1783, we had the poisons in the UK and in Europe, and then global cooling because these sulfide particles got up into the stratosphere and blocked the sunlight. It stopped the monsoons, which depend upon a temperature differential between the continents and the ocean. Without monsoons, the Nile didn't flood, and over 600,000 people starved to death in Egypt because of it. And in fact, there were famines in both India and Japan that were partially caused by this, that killed over 11 million people.
Do we know what the likelihood is of having another eruption somewhere like this?
The probability is 100%. Just give us enough time. And of course, whether it happens this year or next century, that's a random distribution. There are many volcanoes around the world that are capable of doing this, that have done it in the past, and it's absolutely certain that it will happen again. Now, because of modern technology, if we instrument a volcano, we are much more likely to be able to predict that it's happening. But you need the instruments, you need a warning system to communicate. And as we just saw in Guatemala, you've got to be able to get the warning to the people who are actually going to be affected. And that takes time, and sometimes you don't have enough time. So we really need to be ready for that humanitarian crisis. We need to have resources to help the people because it is going to be happening at some point.
Well, let's hope we're prepared for it if we do see history repeating itself. Thank you. That was Lucy Jones from the California Institute of Technology. And thank you to all our other guests this week, Jess Johnson, Anna Young and Evgenia Ilinskaya.
And to finish this week, it's time for Question of the Week. And Marika Ottman is weighing in with this inquiry from Chris Taylor that's quite literally out of this world.
3, 2, 1, 0, and liftoff.
If there's no gravity in space, then how do astronauts weigh things?
Weight is calculated by multiplying mass by the acceleration due to gravity. In space, however, there is very little gravity, also known as microgravity. So perhaps the more important question to be asking is, how do we measure mass in space? On the forum, Janus suggests that since mass does not depend on gravity and weight is really just a measure of the force of gravity acting on your mass, they just provide another type of force to replace gravity. Well, who better to ask than someone who has been weighed in space themselves? I spoke with former NASA astronaut and commander of the International Space Station, Michael Foale, to assess the gravity of the situation.
Normally, we do not weigh things in space, and we use density and volume to estimate mass. However, knowing an astronaut's mass during a long expedition to the International Space Station is critical to understanding how humans can endure microgravity. On the ISS, I used a device called the Body Mass Measuring Device. It was actually built in Russia. There's also a US device called SLAM-D, which stands for Space Linear Acceleration Mass Measurement Device. Both the methods are similar, and they measure the inertia of an object by shaking it.
Inertia is Newton's first law of motion. It states that an object in motion will stay in motion unless acted upon by an external force. So let's say you're in a car and it stops short. Your body will keep moving forward and stay in motion until your seatbelt stops you, which acts as the external force. Your inertia is the measurement of how much your body resists the seatbelt and is directly proportional to your mass.
The method for measuring human mass involves oscillating the person on a table attached to a stiff spring, given an initial amplitude of about 0.3 meters. Once the mass, i.e. the human, is set in motion, the period of the motion is timed, around 3 seconds, and used to determine the mass, which is proportional to the square of the period of the oscillation.
So imagine wrapping yourself around the top of a mechanical pogo stick that moves up and down rhythmically. You'd best hold on tight.
The trickiest part of the operation is getting the person to be as compact and as rigid as possible during the measurements, because they're being shaken around. The accuracy of the measurements is roughly plus or minus a kilogram. When I first tried to use it, I found I moved too much involuntarily. After some practice, though, I could get 3 consecutive measurements to be within a kilo of each other.
Thanks, Michael, for that stellar answer. Next week, we're battling boredom with this father and son duo.
Hi Naked Scientists, this is Thea Hall.
And Simon Hall.
And we would like to know why people get bored.
And what's the evolutionary advantage of boredom for humans?
Oh, that is a good one. But obviously, listeners of The Naked Scientist don't even know what boredom is. Now, if you think you know the answer at the same time, you can email chris@thenakedscientist.com, find us on Facebook, tweet @nakedscientist, or join in the debate on our forum. That's thenakedscientist.com/forum.
And that is it for this week. Thank you to Izzy for putting the programme together. Meanwhile, do go on and enjoy the World Cup. But join us again next week when we'll be getting to grips with addiction. We're asking, are the internet and gaming really addictive? And if so, how many people might be hooked? Let us know your perspectives. You can email chris@thenakedscientist.com. The Naked Scientist comes to you from Cambridge University and it's supported by the EPSRC, the STFC and Rolls-Royce. I'm Chris Smith. Thank you for listening and until next time, goodbye.